beneath Mount St. Helens is about to blow. It's all after the area saw hundreds of recent earthquakes. So is there cause for concern?
300%. That's how much the risk of a sudden eruption at Mount St. Helens has just increased. For decades, this volcano has been a ticking time bomb, and now it's louder than ever.
Some people were describing that lightning and in the belief that it was fire coming out of the mountain. We're expressing it in those terms, but later it was confirmed that that really was lightning that was creating those flashes inside.
Scientists are seeing signs, unusual seismic activity, hidden magma movement, and strange chemical signals that point to a brewing threat beneath the surface. What's driving this dramatic escalation, and what could it mean for the millions living in its shadow? Stick around because the answers might just change the way we think about living on a restless planet. When volcanoes collaborate, imagine waking up to a world forever changed, skies darkened, landscapes obliterated, and a looming sense of helplessness in the face of nature's fury. It's not just the stuff of movies or distant history, it's a reality humanity has faced time and again. Natural disasters, unpredictable and often catastrophic, remind us that we live on a planet brimming with forces far beyond our control. And perhaps no force is as awe-inspiring or as terrifying as a volcanic eruption. Take Mount St. Helens. To most, it's a name synonymous with destruction, a sharp memory etched into history books. The 1980 eruption unleashed an unimaginable fury, obliterating 230 square miles of pristine forest in moments. 57 lives were lost that day, and countless others were forever altered. But what if we told you the real story of Mount St. Helens isn't in its past, but in its hidden depths? Over decades of exploration, researchers have used seismic imaging, ground-penetrating radar, and satellite geophysics to delve deeper than ever before. What they found is a sprawling underground labyrinth, a vast network of magma chambers, fault lines, and enigmatic geological structures stretching miles beneath the surface. These pockets of molten rock form a vast supervolcanic system interconnected with other volcanoes in the Cascade Range. Yes, you heard that right. Mount St. Helens isn't just a singular volcano. It's part of a larger system. This network allows magma, heat, and gases to flow between volcanoes, creating a chain reaction waiting for a trigger. While scientists have long theorized the existence of interconnected volcanic systems, the complexity and scale of what's beneath Mount St. Helens have rewritten the rules. This discovery extends far beyond Mount St. Helens, shedding new light on the relationships between neighboring volcanoes in the Pacific Northwest. This volcano is part of a unified system that includes Mount Rainier, Mount Adams, and possibly even Mount Hood. Think about that for a moment. Volcanoes, once thought to operate independently, are now understood to be connected by a vast underground network. The implications of this are staggering. What if one eruption could trigger another, creating a chain reaction? The Pacific Northwest, a region home to millions, could face devastation on a scale we've never seen. And it gets even more unsettling. Beneath Mount St. Helens lies an enormous magma reservoir, far larger than anyone had imagined. How large? Large enough to fill the Grand Canyon multiple times. Just let that sink in. The sheer volume of molten rock combined with this interconnected system has led some scientists to raise the alarm. But it's not just the size of the magma reservoir that's concerning. Beneath the surface, scientists have detected unusual seismic activity, swarms of small earthquakes and deep tremors originating miles below the Earth. These aren't random events. They're thought to be caused by magma and gases shifting and surging through the underground network. Even more worrying, this activity has been increasing in recent years, leading experts to wonder, is Mount St. Helens gearing up for something bigger? The warning signs don't stop there. Around the volcano, high levels of volcanic gases like carbon dioxide and sulfur dioxide are escaping into the atmosphere. These gases are not only signals of heightened activity, but also dangerous in their own right. An eruption could release massive quantities into the atmosphere, disrupting ecosystems, affecting air quality, and even contributing to global climate change. But perhaps the most unsettling discovery at Mount St. Helens isn't geological, it's biological. Deep within the volcanic caves and tunnels, scientists have found something extraordinary: life. microbial life forms previously unknown to science. These extremophiles, as they're called, are marvels of resilience. At first glance, the discovery of these bizarre microbes deep beneath Mount St. Helens might feel like a fascinating footnote, a quirky bit of science. But the implications are far more profound. These tiny microbes thrive in extreme heat and acidity, hint at something much bigger. Could similar organisms exist in other harsh environments, like the crushing depths of the ocean, or even the barren landscapes of other planets? It's a question that takes us from the volcanic caves of Earth to the very edges of our imagination. The genetic adaptability of these microbes is both fascinating and potentially dangerous. Imagine if these organisms, built to withstand extremes, found their way into ecosystems, agricultural systems, or even human populations. How would they interact with us? Could they outcompete native species or introduce new challenges to public health? Scientists are racing to understand these possibilities, but the risks are undeniable. But the bigger picture lies in what these microbes might reveal about the very nature of life itself. Some researchers believe that extremophiles like these could offer a glimpse into life's origins, evidence of how life began on a volatile early Earth. Could they represent the planet's most ancient inhabitants? Others warn of a more alarming possibility. Their resilience might make them resistant to current antibiotics and treatments, presenting a threat that's eerily reminiscent of modern pandemic fears. Mount St. Helens is more than just microbes or magma. It's a complex puzzle layered with mystery. Strange magnetic anomalies have been detected around the volcano using satellite and ground-based sensors. These anomalies could indicate the presence of unusual mineral deposits or even metallic structures hidden deep within the mountain. While many scientists believe this is the result of natural geological processes, others have ventured into more speculative territory. Could there be something ancient or even extraterrestrial buried beneath the mountain? The assumptions might sound far-fetched, but it's not entirely without precedent. Mount St. Helens has long been a place of legend and lore, especially among Native American tribes who have called the region home for centuries. In tribal stories, the mountain is more than a volcano. It's a sacred place guarded by powerful spirits. Some believe it's a gateway to another realm, where the physical and spiritual worlds intersect. When Mount St. Helens erupted in 1980, it wasn't just the Pacific Northwest that felt its wrath. The entire planet did. The explosion sent massive amounts of ash and gases into the atmosphere, disrupting global climate systems and temporarily cooling the Earth. Now imagine that, but on a much larger scale. A major eruption today could wreak havoc far beyond the blast zone, altering weather patterns, reducing agricultural yields, and worsening the effects of climate change. But it's not just the climate at stake. Mount St. Helens is dangerously close to major cities like Portland and Seattle, home to millions of people. A large-scale eruption could lead to widespread destruction, homes buried in ash, roads and bridges rendered impassable, and critical utilities wiped out. The human toll would be unimaginable, and the economic damage, potentially in the hundreds of billions of dollars. So what's being done to prepare? Scientists and emergency planners are working tirelessly to decode the volcano's secrets. They're monitoring seismic activity, gas emissions, and other subtle signs that might signal an impending eruption. But here's the catch. Volcanoes are notoriously unpredictable. Despite the best technology and expertise, pinpointing when or if Mount St. Helens will erupt again remains a challenge. And that uncertainty leaves communities vulnerable, living in the shadow of a ticking time bomb. Even if an eruption doesn't result in a massive explosion, it can trigger something equally deadly: lahars. These destructive mud flows occur when an eruption melts the snow and ice at the summit, sending torrents of mud, rock, and debris hurtling down the mountainside at speeds of up to 60 miles per hour. Entire towns lie in their path, and history tells us this isn't just a theoretical risk. Lahars from Mount St. Helens have devastated the region multiple times before. But Mount St. Helens isn't just about the dangers we see on the surface. What lies beneath tells an even more fascinating story. What powerful forces shape this volatile giant? And how does it fit into the larger saga of the Cascadia volcanic arc? A geological rebel, Mount St. Helens is not merely a singular wonder, but a chapter in a much larger story stretching from British Columbia to Northern California. This simmering range, known as the Cascadia Volcanic Arc, owes its existence to one of Earth's most powerful tectonic forces, a subduction zone. Imagine this, a dense oceanic plate plunging beneath a lighter continental plate, a collision of unimaginable scale happening miles beneath our feet. As the oceanic slab descends, the pressure and temperature skyrocket, causing fluids to escape and melt the surrounding mantle rock. This molten magma, lighter than its surroundings, begins its slow, forceful ascent, eventually breaking through the crust to form the volcanoes we see today. Most of the Cascade volcanoes form in a predictable pattern, rising above areas where the subducting plate has reached about 62 miles deep, just the right depth for the magic of magma formation to happen. But Mount St. Helens? It's a rule breaker. This infamous peak is located tens of miles west of the other volcanoes in the range, perched above a section of the subducting plate that's only 42 miles deep. It's a geological oddity, one that has puzzled scientists for decades. In the summer of 2014, researchers set out on a bold mission to crack this mystery. Using advanced seismic imaging techniques, they aimed to peer beneath Mount St. Helens and map its subterranean secrets. Think of it like a planetary ultrasound, using the speed and pathways of seismic waves to create detailed pictures of what lies hidden underground. Armed with a fleet of seismometers, they meticulously placed these devices across the landscape, creating a network capable of capturing the faintest seismic whispers from deep within the Earth. This ambitious effort aimed not only to solve a single puzzle, but to unlock a deeper understanding of how volcanoes like Mount St. Helens form and behave. The data gathered offers a glimpse into the unseen forces shaping not just this volcano, but the entire Cascadia Range. And with every discovery, scientists come closer to answering the fundamental questions about our restless planet. How do these fiery giants come to life? And what do they tell us about the world beneath our feet? To uncover these answers, scientists have employed innovative techniques. In one part of the analysis, researchers detonated controlled blasts near the volcano, watching how the seismic waves rolled through the Earth. Like ripples in a pond, these waves revealed clues about what lies hidden deep underground. Meanwhile, other instruments quietly recorded every tremble around the peak for 2 years. These sensitive devices picked up everything, from the distant rumble of ocean waves to earthquakes on the other side of the planet. Together, this wealth of data painted a vivid picture of the subsurface, offering insights into the forces at work beneath Mount St. Helens. But the investigation didn't stop there. Another team analyzed the chemistry of the rocks themselves, melting samples of erupted material under lab conditions to mimic the extreme pressures and temperatures found miles below the surface. And still more researchers use the Earth's magnetic and electric fields to map the conductivity of the underground environment, creating detailed models of how the subsurface is structured. What they found was astonishing. Seismic waves slowed dramatically in a zone east of Mount St. Helens, roughly 10 to 20 miles deep. This sluggish movement could be due to differences in mineral composition, but it could also point to magma. The analysis suggests that while most magma in the Cascades forms deep beneath the other volcanoes, some diverts westward, squeezing through the subsurface to fuel Mount St. Helens. The rocks themselves confirm this story. The sticky, gas-rich magmas responsible for Mount St. Helens' explosive eruptions appear to originate near this deep reservoir. In fact, after the massive 1980 eruption, researchers believe they may have detected tremors from this very zone as the Earth adjusted to the sudden draining of molten rock. For nearly a year, faint quakes rumbled southeast of the peak, likely caused by subterranean shifts in the magma system. But the rumbling quakes and draining magma only scratched the surface of Mount St. Helens' story. Beneath the explosive peaks lies a landscape shaped by ancient collisions and tectonic scars, clues that reveal the origins of its fiery lifeblood. Geological scars and magma paths. The story of Mount St. Helens is written not just in eruptions, but in the ancient choreography of tectonic forces. The choreographer of its magmatic dance remains a subject of debate, but clues can be found in the scars etched across the surrounding landscape, marks left by millions of years of tectonic jostling that continue to shape the flow of molten rock today. One of the key players in this story is a volcanic plateau known as Silesia. Around 50 million years ago, Silesia set off the west coast of North America, but the relentless shifting of Earth's tectonic plates slowly closed the gap. As the ocean between the two landmasses disappeared, the seafloor sediments were scraped together like pieces of a puzzle, compressed into stone, and eventually slammed into the continent in a dramatic collision. That ancient merger left behind an indelible scar, a tectonic suture that scientists believe lies just beneath Mount St. Helens. To uncover this hidden feature, researchers turned to a method called magnetotellurics, which maps the conductivity of rocks beneath the surface. Certain minerals, like those rich in carbon and sulfur, characteristics of marine sediments, light up like a Christmas tree in these scans. And sure enough, just beneath Mount St. Helens, the researchers found a glowing swath of rock. These illuminated zones likely mark the remnants of ancient marine sediments transformed into a unique rock type known as metasedimentary rock, a geological legacy of Silezia's collision with the continent. The surprises, however, were far from over. The analysis also revealed a vast area of low conductivity rock sitting just east of the volcano, above the region where deep magma may pool. This formation, the researchers believe, is a slug of cooled magma that solidified millions of years ago, long before Mount St. Helens ever erupted. It's a relic from a time when the forces beneath the Earth were laying the groundwork for the volcanic activity we see today. Beneath Mount St. Helens lies a complex interplay of forces, an underground labyrinth where ancient rock formations and molten magma are locked in a delicate balance. At the heart of this story is a volcanic plug known as a batholith, a massive body of cooled magma that solidified deep underground millions of years ago. Its unique properties, when combined with the surrounding metasedimentary rocks from the ancient suture zone, may be shaping the very flow of magma beneath the volcano. Here's how it works. The batholith acts like a barrier, preventing magma from rising to the east of Mount St. Helens. Meanwhile, the metasedimentary rocks, remnants of marine sediments scraped together during tectonic collisions, may serve as a kind of relief valve. These rocks provide a path for the volcano's sticky, viscous magma to make its way to the surface, fueling the eruptions that have shaped the landscape for centuries. But there's another player in this underground system, a dense wall of rock beneath the metasedimentary layer, revealed by the seismic array. Researchers believe this dense formation could be part of Silezia's lost landscape, serving as a natural stop to magma flow, directing it westward toward Mount St. Helens. Together, these features create a complex network of paths and barriers, guiding the magma like water through a maze. Even with these revelations, the picture remains incomplete. The deeper scientists look, the harder it becomes to piece together the story. As volcanologist Seth Moran puts it, one of the general rules in geophysical imaging is the deeper you go, the less you know. Still, each new discovery adds clarity to the mysteries of Mount St. Helens, revealing how ancient tectonic events and underground formations continue to influence the volcano's behavior today. It's a reminder that the forces shaping our world operate on timescales far beyond our own. And the story of Mount St. Helens is just one chapter in a saga that's been unfolding for millions of years. Today, the remnants of Silesia, the ancient volcanic plateau that collided with North America millions of years ago, are scattered and hidden, buried beneath solidified lava flows and forested soils. To see it with your own eyes, you'd need to travel tens of miles west of Mount St. Helens, where fragments of these rocks lie exposed. But pinpointing the exact location of the suture zone, the geological seam that influences magmatic flow, remains an ongoing debate among scientists. It's not something you can easily put your hands on at Mount St. Helens, explains seismologist Eric Kaiser of the University of Arizona, which is dedicated to unraveling these mysteries. Instead, the researchers must rely on a flood of data from their studies, analyzing everything from seismic signals to rock chemistry, piecing together clues like detectives solving a geological mystery. And the questions keep coming. How does the magmatic system evolve over time? How quickly does the molten rock travel through these underground pathways? How does such a vast zone of partially melted rock focus its energy into a single volcanic vent on the surface? According to seismologist Helen Januszewski of the University of Hawaii, each potential answer adds to our understanding of why and how volcanoes erupt. Since the catastrophic eruption of 1980, Mount St. Helens has stirred to life multiple times. And as communities continue to grow in the shadow of this iconic peak, the stakes have only gotten higher. That makes monitoring Mount St. Helens not just a scientific pursuit, but a critical task for public safety. Mount St. Helens is being monitored really well, Januszewski emphasizes. Advances in technology have allowed scientists to keep a vigilant watch, tracking every seismic tremor, gas emission, and subtle change in the mountain's surface. Each piece of data helps prepare for the next potential eruption, ensuring that the lessons learned from 1980 aren't forgotten. As scientists race to uncover its secrets, one thing is clear: the next chapter in Mount St. Helens' story could arrive without warning. What do you think lies ahead for this iconic volcano? Share your thoughts in the comments below. If you found this deep dive into Mount St. Helens fascinating, give this video a thumbs up and subscribe for more incredible stories from the natural world. Don't forget to hit the notification bell so you're the first to know when we uncover the next big mystery. Thanks for watching and stay curious.